I guess might as well make a full table here for this. For theta equals theta max, mg sine theta is exactly equal to this. And for angles that are smaller than theta max, mg sine theta is less than that. But of course, mg sine theta is now what the frictional force goes with. It does what it needs to do. Okay, so if you understand those three boxes, you're in very good shape in terms of understanding this system. Question?
So when theta equals theta max, is that at the point like just before it would start to slide?
Correct. So the friction is able to cancel off the force that's trying to move it, but it's able to cancel it off with every bit of effort that it has. So theta max represents the largest angle to which it would not slide. Okay. Okay. Any other questions on this? Okay. So the final order of business I wanted to talk about is what is the deal with having to rate the roughness twice? Okay. Why do we need two coefficients of friction? So I want to compare static and kinetic friction. Now this might seem like a little bit of a silly comparison because as we talked about, you would never want to use them both simultaneously, use one or the other, but it's still instructive to compare them as we will see. So first let me try to appeal to common sense, okay? I want to take an object from rest, like this table, and I want to take it from rest and I want to get it moving, okay? If you ever had to move a heavy object, you probably already know this. So we can talk about the force that is needed to get it moving. Of course, we're going to have to overcome static friction. And we can also talk about the minimum force required to hold it in motion once it's going, right? So there's the initial oomph that you need to go to get it moving, and then there's the force needed to maintain it moving and not stopping. So this is the force that is needed to start the motion versus the force needed to, I should say the minimum force needed to maintain motion. Now, if you've ever tried this, you will probably find, just anecdotally, that the relationship is like this, okay? It's much harder to get the motion started than to then maintain it once you have it going. So, for instance, if you're trying to move something heavy, you have a brain, and what you do is you push it harder or give it a little extra oomph to get it started. And then once you do that, you decide to push a little less, right? Because you don't need to push as hard to keep it moving, right? So, of course, you are applying a force that differs in time. You push harder at first, and then you back off, okay? Well, how much force is needed to start a motion? Well, you, of course, have to overcome static friction, right? So you have to exceed this value. So it's slightly more than this. A vanishingly small amount more than that. Whereas once it's moving, the amount of force that is needed to be maintained, the only thing you have to do is make sure that the, I guess I can draw it over here. So I guess that if it's at zero motion first, you need to push slightly more than the force of static friction at max Whereas once it is moving, if you don't want it to slow down, you have to push as hard as the kinetic friction force, right? So if you push as hard as the kinetic friction force, what's the net force? 0. So what happens to the motion? It just stays like that, right? It won't slow down and eventually stop. You don't need to push harder than that. That would just make it go faster. The bare minimum you need to not have it slow down back to a stop is to push equally hard to the kinetic friction force. Well, which is that? Now, if this inequality is to hold, we can cancel off the common ingredient, and what we find is that the roughness, mu sub s, and roughness mu sub k, they're always in this relationship. So if we rate the roughness twice, the surface is more quote-unquote rough when they're stationary, and they're quote-unquote less rough. So how can we understand this? Well, here's how. When an object is at rest with respect to a surface, they have a chance to get a little more acquainted. Okay? So friction is ultimately born from these temporary chemicals, very small chemical bonds, and they get nice and acquainted when they're stationary. When you are sliding, you just don't have a chance to form as many. I guess let me kind of exaggerate the difference. And the reason why is that because you're always sliding over the surface, it's kind of like Rice Krispies. You're kind of always breaking certain bonds and about to form new ones, right? So you just don't have a chance on average to have as many. That's why friction is a little bit weaker when you're sliding across the surface. You just don't have a chance to get that acquainted with any part of the surface you're sliding it across, okay? Does that make sense? Okay, so this does have a few practical implications we need to be aware of. Let me say that I apply a constant pushing force to an object at rest. So we are going to apply a constant force to an object that's sitting at rest. And there's only a couple possibilities. Here are your possibilities. Either your pushing force cannot exceed the static frictional force max. Okay, so it's less than or equal to that. And if that's the case, what will happen? If your pushing force cannot exceed the static frictional force cap, it stays at rest. That's one possibility. The other possibility is that the pushing force exceeds this cap, and what's going to happen then? You accelerate from rest. It won't stay at rest. Well, if you're able to overcome that, the frictional force that you have to contend with once you're sliding is even smaller than that. So if the pushing force exceeds the kinetic friction force, you'll not only move from rest, but how will you move from rest? You'll move from rest, and then you'll move, and then you'll have to speed up, right? So you'll have to start from rest, but then accelerate. You'll speed up indefinitely. Those are the only possibilities of what could happen when you apply a constant pushing force. If you're strong enough to overcome static friction, you'll be well undermatched by kinetic friction once you are moving. So that's why when you're trying to move a heavy box of books across the floor, you of course would never exert a constant pushing force. You push harder at first and then you back off so that you can maintain a constant velocity and not have it accelerate away from you and have to run faster and faster to keep up with it. Okay? But remember, this is not an intelligent force that changes over time. This is a constant force. So these are the only possibilities. Okay? And then finally, to close out the discussion, I feel maybe this is helpful to some, confusing to others. I want to give you a sense of what does the actual physical data look like. So if you went in a lab and you measured something about friction, what would you find? So what this is going to be a graph of is basically what we're talking about here. I'm going to apply a constant pushing force. I'll put the amount of pushing force on the horizontal axis, and I'll put the frictional response force. Here's what you would find. If you don't push at all, the static friction force has nothing to do. You push a little harder, static friction can respond and hold you in place. So this here has a slope of 1 because, of course, whatever you do, static friction keeps up with you. Obviously, this can't go on forever because we know at some point friction cannot continue to hold you in place. So there is a point on this graph where it stops. For any pushing forces that are less than that, you're in case 1 that I just talked about. You are not going to be able to move it. But if you push harder than that, then you will move it, and we switch from static to kinetic friction. Okay? So we are pretending that it just switches to some constant value. Okay? It's a weird looking graph. So we have one frictional force that just keeps up with you blow for blow until you reach its limit, and then once you're moving, you just switch to some completely different value that's less. In fact, we can mark on this graph, this is mu sub s times n, and this is mu sub k times n. This is everything from here on forward, that's case 2. That is, in fact, how they measure these frictional coefficients. They're completely just experimentally measured. They measure how far can you go along this line. You find out this value, you divide it by the normal force, and you get mu sub s. That's how mu sub s is determined. Then there'll be another line here. You get the value of that. That's the kinetic friction force. You divide that by n. That is how the kinetic friction coefficient is measured. Now you look at that weird shark fin looking function, you wonder, can that really be real world data? Of course it's not. It doesn't look like that. Okay? Here's what it really looks like. It goes like this, and then it goes like this. So if someone just gave you this graph and said, hey, make something out of that that you can do in the first month of Physics 1. You go, oh, okay, that's kind of rough. Okay? But friction is so prevalent, we have to do something, right? So, first of all, what's going on? The friction force isn't really constant. If you zoom in enough, it warbles. Okay? Why is that? Rice Krispies thing here. Okay? So you continually breaking and breaking old bonds and forming new ones, so the frictional force at a microscopic level is not actually perfectly constant. Okay? So I like to think of it as Rice Krispies. You know Rice Krispies, you put milk in them, they kind of make a steady sound, but it's made out of a bunch of discrete poppings, right? Rice Krispies? You eat this? Okay. We kind of wash that out completely, right? We wash out the snap, crackle, and pop here and just call it constant. There is also another thing which many people point out, that it seems really strange to have like this two-pronged attack, static friction and kinetic friction. So that what the usual question is, so what you're telling me is there's one kind of friction when you're not moving, but if I was moving at like some glacial pace, like 1 millimeter every millennium, I have to use kinetic friction? It seems a little bit weird, right? There's no such thing in nature. It's very rare for something to be that discrete, right? So you might say, if you're moving at some glacial pace, what kind of friction do you use? Well, you of course are exploiting a loophole that I'm trying to not have that be in there for you, okay? So of course it doesn't drop off a cliff like this. There is a region of transition between these two. Sometimes this gets a special name. It's called the stiction region. It's sticky friction. So you're going, yes, you're sliding, but you're sliding so slow, you're in some weird nether region between the two frictions. Have you guys done the friction lab yet with the incline? No? Okay. So I think you guys still do that at some point. And I'll tell you, one of the things you can do to make it work out better is do not have this glacial pace of sliding, okay? You do not want to be in this weird nether region between, it's like kinetic friction, but you're going so super slow, it's more like static friction. You don't want to be in this region, okay? And in fact, we pretend this region doesn't exist in our calculations, okay? So what you do in your calculations, if you stay at rest, it's because of static friction. If you start moving, immediately use kinetic friction, okay? That includes, by the way, even if it moves from rest, okay? Because if you're moving something from rest, if you're exerting a decent amount of force on it, it might spend a couple millimeters experiencing a little more friction. Who wants to deal with that? If it slides 5 meters, most of that 5 meters is going to have sped up enough to where kinetic friction is relevant. So just ignore the static friction part, okay? So I know that may seem counterintuitive, but this is because we're doing these approximations. Even if you push an object from rest into motion, if you push enough force to get into motion, just start using kinetic friction. Ignore the static friction, okay? Static friction is really more for testing if it moves in the first place, okay? So that's what really happens. And all we're trying to basically do is break it into two things. First, what's the maximum static friction can hold? And secondly, what is the frictional force that you have to contend with once you are moving, which we call kinetic. Okay, we're just trying to break it into two formulas, and that's it. We're trying to take a complex phenomenon, and we're trying to just simplify it down to the absolute minimum. Okay. So that is a little bit about the relationship between the two different frictions. Are there any questions on that? Okay, so you can mark a line in your notes. This is the end of homework 5 in exam 1 material, and we'll just keep on going. With that in mind, anyone want to change their mind and ask any questions before I move forward completely? Okay, so wipe the slate clean, but I am not going to do something hugely unfamiliar. What I'm going to do is I'm going to go back and do some real investigation about the force of gravity, okay? So this is the force of gravity revisited. For real this time, okay? Because right now, we've been doing gravity a lot and we know very little, okay? So let me remind you what we know about gravity. We know that all objects are given a constant acceleration by gravity. That's regardless of their mass or anything else. The size of that acceleration is 9.8 meters per second squared, which we commonly abbreviate as g. And the direction is downward, which of course can be encoded in a number of ways mathematically, plus, minus, or something else. And this is true if we are near the surface of Earth. So right now, it's the force that causes the magic acceleration for everybody. We don't know why. We certainly don't know why you have to be near the surface of the Earth, and what would you do if you weren't? What if you were really high above the Earth? What if you were on near the surface of Mars? What would you do then? We don't know. Okay? At this point, my only motivation for this is the fact that you guys were dropping basketballs next to motion sensors in lab, and you measured, yes, it is true, but why? Why is it true? And what is it other places? Pretty much the only thing we know is that air resistance and gravity typically act together, right? When you watch objects, realistic objects flying through the air, it's actually a combination of air resistance and gravity. And so one of the things we said was, okay, if you want this acceleration, this magic acceleration, to be reasonably accurate, you have to have that air resistance is negligible. So we drop rocks and baseballs, we don't drop feathers in paper bags, okay? Because air resistance is too important for those. That's not really knowing much. That's just saying if we want to talk gravity, let's not have something else come in and be a big wrecking ball to the situation. So that, of course, was just the bare bones information so that we could do kinematics problems with it, right? It was one problem where it worked really well with the constant acceleration equations, and it was one where the acceleration was always kind of known. I told you that, and we could run with it. I didn't tell you why that was, but we could do something with it. It was a perfect kind of tool for doing some problems on homeworks 2 and 3. In homework 4, we really didn't help anything. We just simply made this fact consistent with Newton's second law. We just simply said, well, if that's the acceleration it gives everything, this must be the force. So it became the force that would cause this magic acceleration. That didn't help anything. That just made our previous statement consistent with Newton's laws. In fact, it brought up an interesting point that if g is fixed for everybody, what that means is a larger mass has to experience a larger force. So we have this mysterious phenomenon of gravity where it takes all masses and accelerates them exactly the same, no matter what their inertia is, and we're forced to conclude that gravity somehow knows to pull harder on things when they're more stubborn so that they accelerate the same as everybody else. So the forces might look like this. How does gravity know to pull harder on things which need it? How does gravity know to pull harder on bigger masses so that they accelerate the same as everybody else? We don't know yet, okay? So we really don't know much of anything about gravity yet. We just have talked about the fact that it's a convenient constant acceleration problem. You measured that, it was true in lab, but you don't know why. We don't know how to apply it in other places. We were lucky enough that near the surface of the Earth covers all everyday situations, so we can run with it far and wide. But we really don't know a whole lot about gravity at this point at all. So that's where we're backing up, and we're going to start from the beginning. So we're going to talk about Newton's law of universal gravitation. This is not to be confused with Newton's laws 1, 2, 3. Those talk about all forces. Newton came up with a lot of stuff. He came up with most of this course by himself. Okay? This he also came up with is a law for how gravity acts everywhere in the universe. Right? And here's what the law says. You have two masses, m1 and m2. If you have mass, it means you belong to a special club. Okay? This mass that you have is your membership card to a club where you attract all other masses in the universe. And the name of that interaction you have with other things is called the force of gravity. So mass is the property of the object. And the force of gravity describes your interaction with other objects like this. Okay? So mass is your membership card, and your interaction is called the force of gravity. It's always attracted